after today, we'll have 5 classes till spring break because we're not meeting on the Friday. He's gonna say this a number of times. We're not meeting on the Friday before break. I won't be on campus that day. I may or may not be available by contact me. Hello.
Can I sit here?
You can totally sit there.
You hungry, Professor?
I'm not. Why? Do you have something for me? A plethora of snacks. What are those? What's in that bag? Hot something.
Hot fries?
Gut burning.
Have some little bites?
I'm pretty good, thank you.
Blueberry.
Appreciate that. Had this like kimchi noodle bowl at home. Pretty.
Sounds good.
It is really good. I love kimchi.
Is that like what is it?
The noodles are like the momofuku ones you get at Target,
Oh, okay.
and then I just added a bunch of kimchi.
Self-creation.
Self-creation, absolutely. So,
Look at all the selection.
it's quite a selection, but it still doesn't have the indigo beauty in there. Just as I was saying before, or maybe I wasn't even saying it. I don't think I even said this. I just pointed at it and talked about other things. I put up a web work for today's material up, and that'll be open through the end of the semester. It's just one of those things you can get in there and practice what happened today. Highly recommend it. Maybe do it earlier rather than later. And there was no pre-class quiz for today. I thought you deserved a break on that for sure. But for Monday, please, and don't wait until right before class because this is somewhat theoretically heavy. This is limits. So we're moving into multivariate functions. So f of x, y, f of x, y, z, and we're gonna have limits of those functions. Limits are traditionally something that people have a hard time with in general. And they get even trickier when you can approach a point from, when you're in the plane, when you're in the plane and I have f of x, and I wanna take the limit at a point, there's 2 directions I can approach from. When I'm in the plane and I have a point, there are infinitely many ways I can approach a point. So things get a lot more complicated in the plane. And this is what I want you to check out. There's one problem for you to do. It's an exercise in the book, but it's just like, note it's just part A of that question. Does this all sound good? Everybody cool with this? Awesome. Today is somewhat interesting and slightly deep. I want to talk about arc length and curvature. Let's go to length first. So length of a curve, R2 or R3, it's too high. I only wear my devil shirt for you guys, just for you guys. Yeah, I don't know if like they can handle it in my RCC 400. I don't know. Just
What's the class called?
that class, koans, neurons in the space between.
That's an RCC.
Yeah, it's a good class. It's on Zen and neuroscience and nature of the self. It's good stuff. But this is for you guys. This shirt.
Is that R to the M?
Is what?
Is it M? RCC 400M.
Yeah, it's an M. Yeah, I'll actually be running it next spring too. So maybe I'll see some of y'all in there. It's a great class. We do a lot of mindfulness practice, a lot of weird experiments. Love it. All right, let's check this out. So I've got some curve in the plane or in space. Let's see, it starts here. This is R of t. It starts at t equals t naught right there. So that's R of t naught. And then it ends at t1. Actually, can we call these A and B? I think that's just going to make notation a little bit better. Apologies. And B. So this is R of A. This is R of B. I want to find the length of that curve. So now, this curve looks like it's in the plane, but we know the trick. If I want it to not be in the plane, I voila, it is a space curve instantly. So the method we're gonna use here is it's irrelevant whether we're in R2 or R3. So I wanna find the length of this, and the basic plan is gonna be this. I'm gonna cut this up into n pieces. They don't have to be equal. You've seen this before. This is calculus. Cut things up into a finite number of pieces that depends on, so let's see, cut the curve into pieces. And let's put up here the goal. Yeah, I guess I already got the length of it right up here. Howdy.
What's going on?
It is going good. Oh shit, would you hit start on that, please?
Of course. It's already started.
Damn, good. Imagine that. All right, so I'm gonna cut the curve into n pieces, and the way we're gonna do this is by cutting the time interval, or the t interval. So think about how this works. There's really this t space here, and here's a, and here's b, and I run that through this vector value function, r of t, and it essentially takes this line segment and twists it into space or into plane, according to that rule. So what we're gonna do is we're going to cut the t interval into n pieces. So I'm gonna have a equals t sub 0, so that's t sub 0 right there. And then I'm gonna partition this by picking points in the middle. And you should recall this from integration. So there's gonna be t1, there's gonna be t2, dot, dot, dot. Right before the last point, that's t sub n minus 1, and then b is equal to t sub n. So we're gonna have a equals t naught, and then to the right of that, a t1, to the right of that, a t2, dot, 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 t sub n minus 1, less than the final one, which is t sub n, and that's my endpoint. So cut the time interval up. Then I'm gonna look at the value of the function at these endpoints. So let's get some color out here. So r of a is this point right here. R of t1 is this point right there. So let's label that. This is r of t2. And on down the way, this is r of t sub n minus 1. And then there's r of b right there. What I'm going to do is take line segments and draw them between these things. So I'm going to make a polygonal approximation of this curve by just connecting those points. And then let's do a little dot, dot, dot there, pick it up there. So let's notate what we just did there in words so that you got it a little more well-defined. So 2 is we're going to create a polygonal approximation to the curve using nodes r of a, r of t1, on up to r of, let's just do that. I like doing that one right before the end, and then r of b, using these nodes connected with line segments, connected by line segments. So, you know, what this curve will end up looking like is something like this. You can just draw something like that. That's going to be our approximate curve. The more points I had picked, the better the approximation. We're going to do it for arbitrary number of points and let the number of cuts go to infinity. And then we're going to have the perfect length, the exact length. So, what I've got here is line segment 1, line segment 2, line segment 3, on up to line segments of n. So let's label those here. We've got L1, L2, L3, L4, blah, blah, blah. Let's figure out what is going to be the length of each one of those. Now the cool thing is, and let's just do this in 3D, if that's too much, just imagine the z is 0. And you're actually just in the plane, the xy plane. So it just makes more sense to do this in xy z space. So let's say r of t sub I looks like this. It's some vector that has an x component evaluated at the time, a y component evaluated at the time, and a z component evaluated at the time. Let me stop for a minute because the folks are taking notes. And I just want to make sure everybody's with me because you really want to follow this story. Everybody good? Any clarifications? We feel okay? Yeah, you good, Othman? Yeah, awesome. You look happy. You look really happy, man. That's great. So, we're going to say that these lengths, these L's, L sub I equals the length of the ith segment. And let's get that formula out. Now, basically what this is I've got 2 points in space. This one's, or vectors. This is x of t sub I minus 1, y of t sub I minus 1, z of t sub I minus 1. That's this one. And then this one here is x of t sub I, y of t sub I, and z of t sub I. And I want the length between those. So think about Pythagorean theorem. This L sub I is the square root of the difference in the x coordinate squared, plus the difference in the y coordinate squared, plus the difference in these squared. And we've seen this before, and it's going to look like this: x at t sub I minus x at t sub I minus 1, quantity squared. Now I'm going to do this derivation, and then we're going to get a pretty formula. This, hopefully you know by now in calculus, this isn't the form we use. This is how we get to our formula. And then last one, z of t sub I minus z of t sub I minus 1 squared. And square root all that. Super Pythagorean theorem. 3D Pythagorean theorem. We good? I'm going to take, let's, just for notation's sake,
So I
let,
have a question.
oh, sorry, yeah.
To clarify that.
Yes, yes.
That part to your left with the x, yes, that's like the coordinates of each line.
That's the coordinate of the end point here,
Uh-huh.
Alexander, and then this is the coordinate of that point. So you got these 2 points in space.
Okay, and they make up each segment.
Yeah, and what's called, that's L sub I, is the
Which is-
length of that segment, the distance between
Yeah,
them.
yeah, okay, I got that.
Does that help?
Yep.
Cool, good question. So just notationally, because this is gonna get to be a drag, let's call this delta x sub I. Let's call this delta y sub I. Remembering that these depend on t. And then this is delta z of I. So L sub I is square root delta x sub I squared plus delta y sub I squared. Do you feel like a derivative is going to show up? Delta z sub I squared. And those all depend on t. Those are all functions of t. So make a little note here. These are all functions of t. A difference functions. Let's even make it more clear. Difference functions. That word is difference functions of t. Almost done. So the hard part is getting the notation set up. The cool part's about to happen. Because what I'm going to do then is write out the formula for the sum of these lengths. So the approximate length using n cuts is sum I equals 1 to n. These L sub I, so let's actually write that up there, just so we remember where this formula came from. I'm adding up these lengths right here. This is equal to sum I equals 1 to n square root delta x sub I squared plus delta y sub I squared plus delta z sub I squared. Sound reasonable? Just add them up, make sure you're good, and let me pause for a minute so you can contemplate. And we're actually gonna do a little trick. We're gonna, because it kind of looks like I'm gonna integrate, right? I'm cutting things up into little pieces. I'm gonna let the number of pieces go to infinity. I'm adding stuff. I mean, an integral sign is literally a sum sign with infinite pieces. But there's no delta t out here. I'm gonna integrate with respect to t, so I'm gonna force a delta t into this. And the way I'm gonna do that is with a little tricky algebra. So here, we're gonna force delta t sub I into the expression. How do we do that? Well, we're gonna write sum I equals 1 to n. I'm gonna divide each one of those, the inside under the square root, by delta t sub I squared. So this is gonna become a much bigger fraction. And I can't just do that and expect this to be the same. Those are all sub i's. Delta t sub I squared. Notice that I've divided by delta t inside the square root. So let me show you what I did. I put a delta t sub I squared inside here, so I'm gonna multiply by a delta t sub I on the outside. Take a look at that. See if you can see the algebra. To bring this under the square root, I would have to bring it in as delta t sub I squared underneath. Yes, sir?
But what would we force the delta t? What reason?
Why am I doing that? Because I want to create an integral, and if you think about what Riemann sums look like, Othman, they look like you've got your function sampled at some points times the width of the cut that you're sampled on. So this is just a general, that's a great question, like what am I doing here? So I'm looking for a Riemann sum, because then when I take the limit as the number of things, as this delta x sub I goes to 0, it turns into an integral. Does that make sense? Yeah, so that's the general strategy here. Any other questions? Don't forget that is delta t sub I. All right. Got a Riemann sum here. I'm gonna let delta t, bless you, I'm gonna let the number of cuts go to infinity. Equivalently, I'm gonna let delta t sub I go to 0. So the biggest cut width will shrink to 0 as the number of cuts grows to infinity. So we're gonna let n go to infinity, this n. Note that this forces, let's just say this forces the delta t sub i's to shrink to 0. The more cuts I make here, the smaller each cut has to be. And you could kind of do that in a converse. I could say, let's make each cut smaller, that requires more cuts. These are same process, just said different ways. So as I do that, now I've got a Riemann sum. So make a note, that Riemann sum, this is a Riemann sum. So as I do that, as I take the limit as n goes to infinity of this, it becomes integral, and my variable is t, so from the starting t to the ending t, square root, what do these become? What is this difference? So I've got, let's remind ourselves what that is. So I've got delta x sub I over delta t sub I looks like this. It's a function, x evaluated at one point, subtracted that function evaluated at a point to the left, and then in the bottom I've got t sub I minus 1. What happens to that as delta t sub I goes to 0?
It goes to 0.
dt.
Yeah, that's it. Yeah, it turns into a derivative. This is literally the definition of a derivative. So as the bottom, as this difference shrinks to zero, the top also shrinks to zero. But I've got a derivative here. So let's make a note that here, as delta t sub I goes to zero, this turns into dx dt. It's the derivative evaluated at some point t inside there. So this becomes the derivative of x. This is x prime of t squared plus y prime, same thing for all these, of t squared, plus z prime of t squared, dt. The delta always becomes a dt. So this is our exact, this is how you find the exact length. Curve. This is the formula we want. So we just had to pay a little. We'll never do that again for a while. It'll be weeks. But when we do multivariate integration, you'll see this process again and again. Like that's literally all you do in Calc 2. The first 2/3 of Calc 2 is these Riemann sums. So hopefully it's not alien. You might not feel like you could get up and give a talk on it, but hopefully it feels like a natural thing to do. All right, let's go and do an example. Is there any questions? Because the example's kind of, this is nice, right? Nice example. We're all good? Let's do something we know the answer of, too. So find the length, and you've got to make these problems really rigged. Otherwise, this part here is undoable. You can easily, if you just made up a random problem with x, y, and z components, you probably couldn't do the integral. So it's got to be a rigged kind of thing. Find the length of r of t equals, and I want you to maybe, oh boy, hold on, am I doing something? Oh my God, yes. Okay, this is not what I thought we would do. But this is what we're gonna do. Yeah, awesome, that's the right answer. That's the right response. Joy. Excellent. And we're gonna let t start at 0 and run to, let's not get, let's get crazy. Let's go up to 10 pi. First, I'd like you to take your vast knowledge of space curves, and without using Desmos, what does this look like? So take a, yes, yeah. So wait, yeah, what was that? I see spirals?
Oh, it is.
Like a spring.
It's
Like a
spiral
spring?
across the x-axis.
It's a spiral down the x-axis, absolutely. So, circle, right? Circle, x position. So in the YZ plane, we've got a circle. The YZ trace, in fact, use the word, YZ trace is a circle, a unit circle. This is moving the circle out as it spins. So what is r of 0? Let's get that. That's going to be 0, 1, 0. Cosine of 0 is 1, sine of 0 is 0, t is 0. So we've got x, y, maybe I'll angle that so we can kind of see it, x like that. So we start at 0, 1, nope. 0, 1, 0, so we start right there. And then just little tips, if you make these hash marks parallel to the other axes, it gets that dimensionality that we're always kind of looking for in these. We know it's a spiral in the YZ plane, so it's going to be kind of like this, moving out this way. Does it move If I'm looking at the YZ plane, is it gonna spin counterclockwise or clockwise? So looking down the x-axis, because we know it's moving out this way. Which way is it spinning? What's that? What do you think?
Clockwise.
What'd you think?
I said clockwise.
Why do you say that?
Certainty. It
Because
just
there's
kinda
like, because
sounds
it's
right.
one or the other?
It just kind of sounds right.
It does sound right.
I got no basis for it.
I would say it's counter the right answer.
Thank you.
So counter.
I'll never forget now, and I won't have to guess anymore.
It goes counterclockwise. And how do I know that? Because the next point, so let's move up to r of pi over 2. That would be the 90-degree rotation. We're at pi over 2. It's like 1.7, no, 1.57. And then cosine of pi over 2 is 0, and sine of pi over 2 is 1.
So would it be clockwise if we just switch the Y and Z component?
Yeah, absolutely. Yeah, if I switch these, yeah, I think so. Yeah, because then this would go first and then that. Yeah, I think that's what would happen. So the next one, here's pi over 2 right here. It's like 1.6. And then I'm gonna go no units over, but 1 unit up. So if I make that 1 right there. So that's my next point, and what happened was I spiraled through space to get there. And then it's gonna, that's not great, because then it's gonna go under, down, loop around, come over.
Very good.
Thanks. Oh, thanks. I appreciate that. It's nice. You can see it, right? That you can kind of see what it's doing. The coiling, it looks like it's getting tighter. It shouldn't get tighter. It should maintain the same coiledness. So in that sense, I'm not super happy with that. But do you see what it's doing? Spin it out this way. And then what's our last point? It's going to be 10 pi. So r of 10 pi is equal to 10 pi. What's cos of 10 pi? Should be 0. 1. Should be 1. Indeed. And then what's sine of 10 pi? 0. Yep. So we end up somewhere out here. We end up x here, then y. So we're kind of ending up eventually dot, dot, dot. We end up like right there. There's stuff that happens in between, but we come up and we're right at the 10 pi mark. So this is r of 10 pi right there. Here's r of 0. Yeah, a lot of stuff happens in between there, lots of spinning. So we're gonna find the length of that, which sounds kind of amazing, actually. If it was just a circle, we'd be good. Because we know how to find the circumference of a circle, but this ain't. So let's use our formula. So the length, and this gets super easy at this point. All right, so length, let's do brick red. So length is going to equal the integral from 0 to 10 pi of the square root. So this is x, this is y, this is z. I'm going to take the derivative with respect to t. So what's dx dt? 1 squared. Perfect. Plus, what's dy dt? Minus cos. Minus sine, sorry. Somebody said that, I think. I'm not sure if they did or not, but we'll go with that. And then what's dc dt?
Cosine squared.
Cosine t. Squared dt. Can you do that integral? Take a minute, please. I would simplify it or use a cool fact.
Yeah, there you go. That's it. Yeah, you see what I mean? Yeah, yeah. I wouldn't do that to you otherwise. I'm not gonna make you do a trig integral that requires substitution or anything.
And then
You just add
it's gonna be yeah, right? Cause like the integral of like a constant, just add it back, but
Yeah, just for,
variable, and you just get.
I just made two to the 1/2. Which I guess that works too. Something probably equivalent if they were to
I'm sure.
do them, but. I guess
Wait,
I
how
have
did you
T-
integrate?
I have 2 to the 1/2. You do T to the 3/2 over 2/3 or times 2.
That's good.
But then I need to plug in 10, whatever.
Because you're integrating in terms
I like
of
that you
t,
use the
do we
1/2.
want to do that?
That's good.
Yeah, you should be able to.
What you got here?
Yep, perfect.
I just couldn't read. That's
Yeah.
another something weird, but yeah, that's, yeah, if it says that, then that's,
I think that's.
you think?
Well,
What's
no,
the
this should-
4/3?
Oh, it's 10 pi root. Cause I had 2 to the 1/2.
Yeah, that's just
So
square
it-
root of 2.
Yes, then I had 2
Oh.
t to the 2/3 or something.
Look at that.
Three
Okay.
times.
Oh, you should, that's a constant. If that was
I know,
t,
yeah.
oh, okay, you,
Mhm.
but so there's no actual t
Yeah.
integration that would take place.
Mhm.
Does that make sense?
Yeah, yeah.
Okay, cool. Okay.
I like this better. Put the pi after.
Yeah. Oh, yeah, I like that too. I kinda like that. That's the order I'd probably go for too.
Yeah, that's good. They're both good.
There's nothing wrong with either one of those.
Eric's got some magical tone writing going on here.
Yeah, I see. Yes, yep, absolutely. Looking good. That's good.
Just do hard.
We gotta use the sine squared plus cosine squared is 1. You know I'm gonna use, that's gonna show up, like it's just, cause I love it, it's beautiful, why wouldn't we use it, it's so cool. And it makes this problem like, holy shit, that was easy. Kind of shockingly easy. So then you could either realize that's just, 10 pi times root 2, or you could go through the full, I'm gonna take the antiderivative, evaluate from 0 to 10 pi, and then you get square root of 2 times 10 times pi. So I saw it once written this way. I like that.
That must have been really smart.
That guy, I was like, yeah, I knew it. It was glowing.
Sorry.
How do we feel on this? And then that's units long, whatever units are, who knows? Who cares? We're in calc. Oh, I guess I shouldn't say that. One day it'll matter. What's a weird unit of length? Angstrom? Is that a length? No, that's is an angstrom a length?
Yeah.
Yeah, so angstrom. And then what is that like A, like that or something?
Is that like the amount of land a cow can plow in a furlong or something?
Yeah, exactly. Divided by the cubits
Yeah.
of length in the cow.
Yeah.
Yes.
Something like that.
That's hilarious. The most random piece of knowledge.
I think it was made up knowledge, just to be safe, yes. Yeah, that is not what it is. I think it's the wave, it's like some wavelength of
I
light.
think,
kind of
there
thing.
is a
It's
unit
like-
of measurement that's like how long a cow can pull in a furlong or something.
What is that really
I
something?
think it is, yeah.
Oh, look it up.
What that unit is. That sounds so fun.
Huh. That's pretty good.
What is it? I'm gonna look up what an angstrom is.
Yeah, look up angstrom, because I think it is, sorry.
It's actually like how long a cow takes to plow.
It's a very tiny cow if it has anything to do with angstroms.
Yeah.
It's 1/10,000,000th of a meter is an angstrom.
It's tiny.
Very, very small.
Okay. Cool. We needed physics knowledge. You were gone.
You guys want this
I-
time?
Wait, no, that's what a furlong is. A furlong is how long a cow can pull in like some amount of time. And then,
Oh, okay.
or like a fortnight or something.
Fortnight's 2 weeks.
Yeah,
isn't
but I
it?
think it's
Oh,
like
that's
a
how, oh,
furlong.
got
I
it,
think
okay.
something like that.
Oh, wow.
Yeah, it's
Okay,
weird.
huh, that's cool, I like that. Things used to be really dumb before the metric system, just insane. Interesting, but unusable.
There's like the unit of barley corns.
To measure the usage.
Wait, now what? Barley?
Yeah, there's a unit of barley corns. It's how many
Really?
barley corns, yeah.
Anything but the metric
Yeah,
system.
exactly.
There's John, I'm thinking of John Barleycorn, which was like a pagan, like, you know, like Burning Man. They would create an effigy of like some guy, John Barleycorn, kind of like a crop god, and then burn him and hope for good crops in that way. Cool. All right, so let's talk about how we're gonna use this. Well, we're about to do something really weird, but it'll make sense once we actually start getting into it. First, let's define this arc length function. Bless you. So I've got this curve R of t, and its parameter t runs from A to B. So it's a line segment. Maybe it's possible that it could be infinite length too. It's all good. But we do have some starting point that we want to think about. So what I want to do is create a function, L of t, that is the length from the start of the curve to any t value. So it'll actually be a function of t that gives me the length for any t that I plug in. So this is going to equal the length of R of t from t equals a to arbitrary t. And the way that's going to work is it's just that integral that we defined, starting at a up to t. So notice here I've got a variable limit on the integral. Variable upper limit. And this is a very different way of thinking about things. We're defining a function, and the function changes the integral limits. I'll stop saying that. And then here we're going to have, let's write this and then define this. So this is going to be the function derivative and its vector length, dt. So why am I writing it like this all of a sudden? Let's actually think about why. So if R of t is x, y, z, and all those are functions of t, then R prime of t is the vector that's just the derivative of all them critters. And the length of this thing is literally that square root that goes under, that is our integrand. So the length of R prime of t is square root of this square plus this square plus this square. So it's just a much more compact way of writing that arc length formula. You stop. Tell me if that's cool, if that makes sense. Just introducing new notation, but more compact. It's just a lot less painful than writing all that stuff. We got this. Okay, so that's the arc length function. We're gonna call that S. So this, you know, like if you have a function y equals f of x, you don't need to have y equals over here, but it helps when you're thinking about input and output. So we're gonna call this S as our output variable. And think of S as like that physicsy thing where it's like position, displacement, right? What is that?
That's separation.
Separation, yeah, works.
You're right, it's displacement.
What's that?
It's displacement.
Displacement?
Yeah,
Nice.
you got it.
I got it under control. And then now it starts to feel, now I'm starting to walk on a bit of a tightrope. And I just gotta be careful. So let's change color to be careful.
See, we found a funny unit.
What's this?
We found a funny unit.
It threw me off.
Slinch.
Slinch?
A slinch.
What's that?
It's like how you have you learned today from Dr. Seibert that pounds divided by like a time is called
a slug.
a slug.
Oh, I knew slugs. I knew
Yeah,
slugs.
this is
yeah.
like the distance measurement equivalent. It's called a slinch.
Wow. Huh.
The inch version of the slug is called the slinch or a blob.
I like blob. That's
So-
good. That's good. I'll try to find a problem that involves that so that we don't understand anything about what's happening. All right. So, got some questions for you. First off, let's actually notice a couple of things. This quantity under here is always going to be positive. We're always going to assume that the r prime of t is not the zero vector. Because when you have the zero vector, what happens is you get crinkling and things are non-differentiable. So for example, it means you stopped. So if I have a function r of t and it stops and then takes off in a new direction, you see that's a cusp. And we want to avoid that. We're looking for smooth trajectories. So this is when r is equal to the zero vector. That kind of stuff happens. So we're avoiding that. We're going to avoid that. So this thing under here is always positive. That means this s function can only grow in length. Think about, you've got an integral. Here's a. And I've got a positive function. And here's t. As t moves to the right, the area can only get bigger. If I have a function that is above the x-axis or the t-axis, if I integrate further out, the value of the area grows, the area grows. So this s of t, I'm going to make some comments here. This s is an increasing function. And I'm going to show it to you in a different way. Of t. How do you use calculus to determine if something's increasing or decreasing? What
Derivative?
Derivative, absolutely. So let's take the derivative of the arc length with respect to t. So that's d dt. Now we're going to see if you remember this weird fact. Oh God, what a weirdo! This can't be t here. Put tau. Sorry. Can't have the same variable of integration as the limit. So I don't want t here and t here. So put a tau there. So r prime of tau d tau. What is that? Fundamental theorem of calculus part. Duh. What are you thinking?
The derivative cancels the integral.
They cancel each other out. So think about how this works. If you have an integral of a function, and then you plug in these limits. So you're going to get the antiderivative of f. Let's call that big F. And it's evaluated at the top limit minus that evaluated at the lower limit. So this big F equals the antiderivative of little f. What happens when I take the derivative of this? Well, this is the antiderivative of little f, so it's just little f of t. This is a constant, so it goes to 0. So when I put d dt out in front of this, as Kayla said, it just undoes the integral, and what I'm left with here is just f of t. That's fundamental theorem of calculus part 2, which says derivatives and integrals undo each other in this order. So this thing right here is just the magnitude of r prime evaluated at t. That's it. That's how fast the arc length is changing. Okay, so now we're going to do some weird stuff. I'm like definitely watching where I step, and I'm also watching the time. We might have to finish this up on Monday a little. That'd be all right? What if we finish this up on Monday, and then we did the skills checks for this stuff on Monday, and just knocked them out?
Okay, sure.
Well, we don't have to either. That's cool, I was just thinking we'll probably have time.
Will you repeat that one just?
I was thinking we could knock out skills checks on the arc length and curvature stuff while we're all here.
Yeah, let's do that.
It actually sounds like a pretty good idea, cause it'll be fresh, right? And then we'll just get that shit done and move on.
Yeah.
Yes?
Well, would we be able to get the skill checks back before spring break since we're taking the Friday off?
Oh yeah, I mean, I'm gonna have the ones you did on Wednesday back on Monday.
Okay.
And the ones that you would take on this coming Monday, there's a lot of classes before the end of, we have like almost 2 weeks.
Okay.
Yeah, does that sound okay?
Got no faith in your grading time, I guess.
Yeah, I mean, I'll probably have it back to you by Friday at the latest.
Okay.
No. But you don't want it if you have to wait, is that what you're saying?
No, I don't know. I was just thinking about it. I just was like, we're taking the Friday off. I just want to make sure we have time.
I got you covered. That means we can't do any skill checks that second week, that's what you're saying. I don't know, we'll see about this, we'll see, well, don't worry, I got you covered. I'll make sure you're happy, Tom.
As they say.
Okay. So, let's think about some problems now, because the main problem I want to talk about at this point is curvature. How do we measure curvature? So let's think about what we might want curvature to be. There's a line. What would we like the curvature of a line to be? Okay. Is it curved? No. So here we would like curvature, let's use kappa, we'll define kappa. Curvature kappa, here I would like a line to have curvature 0, to not be curved. I want it to indicate how bent the thing is. Let's take a little circle versus a really big circle that I can't even see the center of. A little circle, big circle, the radius is like over here, or center's over here. Which one seems like it has more curvature?
Little circle?
Little circle. So this feels like a tighter curve, right? Like if just I were at the size that I'm at, or let's just say I'm in a little ant car. I've got a little ant car and I'm driving around that. I gotta really crank the steering wheel to the right. Gotta really hold it tight right as I drive around there. Whereas if the same little ant car is driving here, I want it to be driving, it doesn't matter what direction it's driving. And same little ant car, it looks a little bigger, but it's the same car. Less turn on the steering wheel here. So the angle of travel here is much less than the angle of travel here. So I want this to have a larger curvature, larger kappa than that to have. So this is kind of what I'm wanting to measure. Now, all the stuff that we're gonna be traveling on, yeah, we definitely need Monday for this. And honestly, if we run out of time on Monday, we won't do the skills checks. I won't do it unless you have enough time. I promise you, I got you covered, I got you covered. These things are all parameterized by t. We think of this as time. Think about how we can parameterize a circle. This little circle here, let's come back to the unit circle. So here's the unit circle, 1, 1, minus 1, minus 1. I could parameterize that as cosine of t, sine of t, and I'm traveling around it. But I could also parameterize it like this, cosine of 100t, sine of 100t, and I still travel the same path. What's the difference? What's the difference in how these particles are moving? Well, yeah, what'd you think?
Magnitude?
In terms of what? Which magnitude? So that could be a right answer.
Frequency is increasing.
What, say what you were saying?
More rotations.
More rotations for sure. In the same amount of time, this would do more rotations. And then what were you saying? Yeah.
Frequency is increased?
Frequency, say, yes, exactly. So we're gonna travel faster.
Velocity.
The velocity. And in fact, let's just do the magnitude of, so the velocity here, r prime of t for this one is just minus sine of t cosine of t. The magnitude of this one is, now that 100 pops out in front, right? So it's minus 100 sine of 100t, and then positive 100 cosine of 100t. And then if I take the magnitude of this, so here the magnitude of the velocity, the speed, is 1. That squared plus this squared. What's the magnitude of the speed here? In this guy? That squared plus that squared.
100?
It's just 100. Yeah, it's just 100. Think about this. This is a circle of radius 100, right? So how far is the magnitude? So this thing's traveling 100 times faster than this one. That's freaking fast. As you guys said, this is a higher frequency, more revolutions. Higher, you said something and it was right, but we just had to get to the right thing. So what I don't want is for curvature to depend on how fast I'm traveling. I want to make curvature independent of the speed at which I traverse the path. And this is where things get a little tricky. So I'm gonna stop because it's 10 till. We're gonna pick this up. Yeah, yes?
With clarification, for the magnitude of R, that bottom one, would it not be 100 squared?
But then you would square root it.
Oh, that's right.
Yeah, yeah. Let's go. I like that you're doing formulas. Yeah, yeah.
Yeah.
So if you want to work ahead, there are some web work problems. Maybe hold off. I'm going to change the skill, the pre-quiz for Monday. I'm going to move that to Wednesday. Okay, there's one because I want to pick this stuff back up. But if you want to practice it, go look in the book. Parameterization, honestly, parameterization by arc length, if that's your homework for the weekend, to read about that. Parameterization by arc length. Because this is heavy. And if you at least just read it or watch a video on it, Google a video, watch that shit, you'll feel a lot better on Monday.
You should do the videos that they put on YouTube, like your organic chemistry. Have you ever seen that guy?
No, I have. I've never watched
He's like
your chemistry. I never watched your chemistry
He's
video.
like, he's a really good like math teacher.
Yeah?
He's like a ton of physics.
What's his name?
Organic chemistry teacher.
Oh, is that really his name?
His YouTube channel. Like,
Look at the
yeah,
guy.
he's like the equivalent.